Hello. Hello. All right, we have 15. I'm going to start. Hello, everyone. Today we're talking about more about simple harmonic motion. And so after today's lesson, you will be able to complete Simple Harmonic Motion Quiz 1. This should be a pretty quick one. So here is what we are what we're going to do. The first thing I want to talk about is that simple harmonic motion must occur about an equilibrium point. And when I say an equilibrium point, I mean a point where the force is equal to 0. Okay? So that's an important point. You can't have, for example, simple harmonic motion if something is on a hill, because it's not going to oscillate about that point on the hill. It's going to roll down the hill. You could have simple harmonic motion about the bottom of a hill, all right, because then it is going back and forth like that. Okay, so for example, what if I have net force equals ma? All right, now what if my net force was k times x minus c? What is going to be the x value? What is going to be the x value that is the equilibrium position? Type it into the chat if you know. What is the x value of the equilibrium position in this case? X equals what? Where is the location of equilibrium? Oh, this should be minus x minus c. Yeah, so if we look at it, if we plug in, so here the equilibrium is at x equals c. All right. Why is that? If I plug in x equals c on the left-hand side, I would get c minus c, which is 0. Okay? So what that means is, omega squared is still going to be k over m, right? If I divide the m over, I get minus k over m times x minus c equals a. So omega squared is still k over m. So the period is not affected, but the location of the equilibrium is not x equals 0. So what that means is that our solution in this case, all right, is going to be x of t equals a cosine of omega t plus phi, but then we have to add in the constant. Okay, so if you think about a cosine function, it oscillates about x equals 0. But if we add this constant, it's going to oscillate about x equals c. So your position time graph is going to look like this. So here is x equals c, and it's going to oscillate about that point instead. So it'll be a shifted sine graph. Okay? So yeah, you can have shifted simple harmonic motion. It still counts as simple harmonic motion. The oscillation has to occur. The oscillation has to occur about an equilibrium point. So one of the things I want to talk about, the second thing I want to talk about today is the so-called ubiquity of simple harmonic motion. The ubiquity of simple harmonic motion. So we see simple harmonic motion everywhere in nature. Ubiquitous means you see it everywhere, okay? Simple harmonic motion is everywhere. That's why it's one of the most important things to study in physics. It's because you find it everywhere. And the question is, why? Why is simple harmonic motion everywhere? Well, what if I had a random graph of potential energy versus position? Okay, so it's just a random graph. Maybe it looks like this. Okay. All right. If we look at it, this potential energy versus position graph, it has two stable equilibria. These 2 points right here are the stable equilibria of this potential, okay? And it turns out that we can approximate, no matter what the global form of the potential is, we can approximate the potential as a parabola near an equilibrium. Okay, so if you have, so see how this graph right here, this dashed line, is a parabola, and that parabola gets really close to the potential at the equilibrium. So this parabola approximates u of x near the equilibrium. Okay. So here we can approximate the potential energy near the equilibrium, okay, with a parabola. No matter its shape, no matter how crazy it is, we can always approximate it with a parabola. All right. Now, I'm not going to give you the details of why this is true, but I'm going to tell you what the approximation is. Okay. So the approximation is, near an equilibrium, we can approximate u of x as u evaluated at the equilibrium plus, I'm going to need more space. I'm going to write this on a different line. So u of x near the equilibrium is approximately equal to u evaluated at the equilibrium plus u prime of x evaluated at the equilibrium times x minus x equilibrium plus 1/2 u prime prime evaluated at the equilibrium times x minus x equilibrium squared. So notice how it has x squared, so it's a parabola. Plus other terms if we wanted to make it a more precise approximation. Okay. U prime, remember we learned that force is equal to negative the derivative of the potential energy. So the force is minus u prime. What is u prime going to be equal to at the equilibrium? So what is the force equal to at an equilibrium point? Type it into the chat if you know. Type it into the chat if you know what is the value of the force at the equilibrium point. Zero, yeah, the force is equal at equilibrium. So this term, this middle term, is going to drop out. Okay? So that term drops out because equilibrium has u prime equal to 0. Okay? So what that means is that near an equilibrium, all right, near equilibrium, u of x is approximately equal to its value at the equilibrium point plus 1/2 u prime prime at the equilibrium point times x minus x equilibrium squared. Okay? So now what I'm going to do is I'm going to find the force near the equilibrium. Now the force is minus the derivative of the potential with respect to position. Okay? So I'm going to take the derivative of this approximation. All right? Now, the potential evaluated at equilibrium is just a constant, right? Because I'm plugging in a specific value for x. So this is a constant. So this term has no derivative. All right? So all I have to do is take the derivative of this second piece. 1/2 u prime prime evaluated at equilibrium is just going to be 1/2 u prime prime. And then I take the derivative of 2 times of x minus x equilibrium squared. That's going to be 2 times x minus x at equilibrium. Okay? Just like taking the derivative of x squared. Okay, the derivative of x squared is 2x. All right, so I took the derivative of x squared and it brings down a factor of 2. All right? So that means that near equilibrium, the force as a function of position, the 2's cancel out, is minus u prime prime evaluated at the equilibrium point times x minus x eq. All right? So what is Newton's second law? Near the equilibrium point. All right? Well, that's going to be force equals ma. The force is minus u prime prime at x equilibrium times x minus x equilibrium. And that equals ma. So I want to compare that with the equation that I gave you at the beginning of class, which was, minus. So I'm going to divide both sides by m. All right. The equation of simple harmonic motion is minus omega squared x minus c equals acceleration. So who can tell me what is omega squared equal to? What is omega squared equal to in this case? I will wait. And there seems to be a lot of lag today between me saying the words and it showing up for you guys. Well, I want you to compare these two. All right, looks like no one wants to answer. So by comparison, we can see that the number multiplying x is u prime prime over m. Okay, so what this means is that the period is 2 pi over 2 pi times the square root of m over u prime prime evaluated at the equilibrium point. All right, so this is our main result for today. So what we've shown is this. Near any stable equilibrium, a particle can undergo SHM. Okay, the particle will undergo SHM near any stable equilibrium, no matter how crazy the potential looks as a whole. Near a stable equilibrium, it can always be approximated by a parabola, and so we will always get simple harmonic motion. Okay, so near any stable equilibrium, a particle can undergo simple harmonic motion as long as the amplitude is small. Okay, what happens if the amplitude is too large? If the amplitude is too large, then the particle is vibrating so much that it goes over the hump into other equilibria. Okay, and so that obviously makes it not simple harmonic motion anymore if it gets stuck over here for a while and then it switches over back and forth. Okay, so if the amplitude gets too big, it's no longer appropriate to approximate the potential by a parabola because you have to take into account the other features of of the potential. Okay. But here's the thing. In nature, a lot of times the vibrations are small. So we are constantly seeing simple harmonic motion in nature. Okay? Anytime you have a system that is disturbed from equilibrium, if the disturbance is small, the system will undergo simple harmonic motion. That's what we've shown, which I think is really neat. And we can see that that the period of the oscillation is related to the second derivative of the potential, which is basically the curvature. So the more sharply curved the potential is at the equilibrium, the greater the period will be. Okay, so let's do an example. All right. Suppose u of x equals 5e to the 2x plus 2e to the 3x. E to the minus 3x. All right. Find the period of small oscillation. About the equilibrium. Now, one thing we have to check is that does the potential even have a stable equilibrium? And I know that this one does, okay? Why is that? Well, if we think about these two graphs, if we think about a graph of e to the minus 3x, it's going to look like this. And then if we think about a graph of e to the 2x, it's going to look like this. And so we're adding these two together, and so the overall shape of the potential is going to kind of look like that. All right? So it kind of has a stable equilibrium somewhere near x equals 0. All right? So the first thing we have to do is we have to find the equilibrium. And so what I'm going to do is I'm going to calculate u prime. So u prime is going to be 10 e to the 2x minus 6 e to the minus 3x. So I'm taking the derivative of an exponential function there. And to find the equilibrium, I should set that equal to 0, because the equilibrium of the potential has 0 slope. Okay? So that means that 10 e to the 2x equals 6 e to the minus 3x. All right. And so that says that 3/5 equals e to the 5x. And then, so that tells me that the coordinate of the equilibrium is 1/5 the natural log of 3/5. Okay, so let me plug that into my calculator. And I get that the equilibrium occurs at x equals minus 0.1. Okay, so now, oh, and let's say that this is of a 1 kilogram particle. So that's kind of the first part. The second part is I have to find u prime prime at the equilibrium. So u prime prime, taking the derivative of this again, is going to give me 20 e to the 2x plus 18 e to the minus 3x. Okay, so now I'm going to plug in 0.1. So I have u prime prime 20 e to the 2 times 0.1 plus 18 e to the minus 3 times 0.1. And that's going to give me 37.7, 37.8. All right. So then to get my period, I would do 2 pi square root, and we said it's a 1 kilogram particle, so I would use this equation here. So I have 1 over 37.8. And that gives me almost exactly 1 second. All right. So that's how that works. So you find the equilibrium, and then you calculate the second derivative at the equilibrium, and then you use this formula to get the period. So I like that. So that's my lesson for today. I will see you in the Zoom room.